So over to Seamus.
Thank you very much, Chairman. So I'm going to begin not with an apology but a statement. I'm not a scientist, I'm not a geologist, so I'm out of place here, but I am an engineer, and I strongly believe that a good dollop of engineering is what is most urgently required. And I come here to bust some myths and to be a radical because none of you understands compressed air energy storage. And many of you will say things about it, and a lot is said about it that isn't true. So my primary agenda is bust a few myths. I'm not going to disclose any inventions today, but I want to set this in some context, because compressed air is regarded as being old, staid, mature, inefficient, and so forth, and all of these things are wrong. And I should say, before I go on too far, I completely subscribe to the message of the previous talk, which is essentially about system, figure out what you're trying to do, and don't jump at particular solutions. This is consistent with that, but I'm primarily going to address, inverted commas, electricity storage. So I'm not naysaying what Professor Peters has just said, but I'm primarily going to address electricity storage. I will give credit to Energy Research Accelerator, which is a project that's running in the Midlands, a £60 million project funded by Innovate UK, which has influenced this thinking, and also to EPSRC, that has funded projects that have involved BGS, and you'll see some reference to that. So my talk rambles, and it's got several sections to it, but I'm going to go quite quickly. First of all, I'm going to explain to you that the cheapest energy of all is renewable energy now. The cheapest electricity of all is now renewable energy. Very few slides. Put some size on the magnitude of the challenge, because it's big, but it's not unthinkable. I'm going to tell you what compressed air energy storage is, and you'll be surprised. And then I'm going to tell you what it is not, and I hope you're even more surprised. I will allude very briefly to the capacity that we have in the UK to store loads of electricity, and I could almost summarize the talk now by saying it's huge. And I will finally link in a way to Professor Peters' talk by saying that you can integrate compressed air energy storage with other things very well, and then what comes next from here. So to begin with, we have passed the watershed where renewable energy is the cheapest form of new generation. This is a graph that was released in 2017 after an auction in Mexico committed to delivering electricity from PV panels at $20 per megawatt hour, in fact below $20 per megawatt hour. And that is the trajectory of lowest PV costs per year. And you know, ordinarily in engineering you expect things to show some kind of asymptote, but this looks like it has every prospect of passing through zero in 2000. And the point is, of course, it won't go through zero, but it will become so low that it's no longer the issue. So we're valuing the wrong thing. There is no energy crisis. The sun is throwing down 10,000 times as much energy on the world as we are consuming. The question is, how do we manage the collection of that in a cost-effective way? And similar is happening in wind, and the last 2 years have been absolutely extraordinary in terms of offshore wind because of the progress that it's made. There was a time in 2013 where the Department of Energy and Climate Change had an ambition to reduce the cost of offshore wind down to £100 per megawatt hour by 2020. And last year there were auctions for offshore wind that came in at £57.50 or something like that. And these are the predictions on here that in Europe, offshore wind is going to be coming in below 40 euros per megawatt hour by 2025. And if you want to set that in the context of nuclear power, and particularly Hinkley Point C, please note £92.50 index linked to 2011. I know it's not the only nuclear power option, but it's sobering. And so I said I was a radical. I am a radical. I believe that we can and should be going towards 100% renewable energy systems, and that we should be thundering for that, not holding back. And I believe that the economics is already going to push us very nicely in that direction. The point was made in the first keynote talk that actually small differences in costs can shift energy systems quite rapidly, and I believe that this is going to happen. We've worked so far extremely hard in renewables at the objective of achieving a small penetration. And in order for renewables to achieve a small penetration into the energy system, what you have to do is to get the levelized cost of electricity lower than coal-fired and oil-fired. And we've done that. It's finished. So that's not, unfortunately, the route for getting us to 100% renewables. Then you have to address something very different, which is to make sure that the electricity is available where and when required. And that's a major challenge. And this is a picture that I drew, and the scales may be wrong, but the general gist of it is definitely correct. If you think about the total cost of energy, it has two components. It's got the cost of generating it, which we know is on an asymptote down, and we know has already passed grid parity. And then it's got the cost of reconciling supply and demand, which is, in this acronym, the levelized cost of storage, if you want. And that's going to be rising. And interestingly, from an economic perspective, the UK hasn't done very well in renewables, have we? We have got no wind turbine manufacturer, we've got no PV panel manufacturer, we've got no significant, well, that's storage, but we don't have any significant battery manufacturer yet. We'd like to change that. We haven't done very well in renewables, but we can do well in the flexibility game, and there is still, it's compatible with expertise that we have in this country. So the message from this slide is the big amount of value in energy in the future is not the megawatt hour, it's actually the megawatt hour. It's the ability to move a megawatt hour by 1 hour. Right, magnitudes and duration. Well, energy storage spans a huge range of magnitudes and time durations. This is a pile of coal outside any power station, any coal-fired power station, of which we have very few left, I'm pleased to say. And that's a terawatt hour in rough numbers. You know, if you look outside a big coal-fired power station, there's a terawatt hour worth of electricity outside that. And that's a battery that you stick in a mobile device, and that's 1 watt hour, 10 to the power of 12 times smaller. This is, in rough terms, how much electricity the UK uses in a day. Roughly speaking, a terawatt hour, a little bit less we use. This is a demand curve, as it happens, this is 2006, I think. But this is energy demand over a 2-week period. And if you smooth out, if you draw a red line in there which sort of smooths out the 1-day variation, you realize that if you wanted energy storage to do that smoothing for you, you're talking about 70 gigawatt hours, roughly speaking. 70 gigawatt hours. And to put that in some scale as well, we have pumped storage of about more than a third, 3/7 of that. And that's our daily consumption, which is about 10 times bigger than that. This is the most important graph that I'll show you, because when people speak about energy storage, they almost immediately assume and think that they're talking about batteries, and Professor Peters alluded to that several times. That's wrong. But, you know, as we introduce renewables into the system, as it starts to penetrate, what happens is, from time to time, the demand doesn't match with supply, and so you need a little bit of flexibility from somewhere. It doesn't have to come from storage, but it can. And we are on the beginning of this journey. You know, we've got some penetration of renewables, but until you get past a certain point, you don't need any energy storage at all. And then when you do get past a certain point, the duration of storage that you need is very small, in the order of an hour, or much less than that. If you look at where batteries have actually penetrated into the UK market at the moment, they're actually penetrating for enhanced frequency response, which is a 1-second service that has recently had a criterion added to it that says you must be able to store for 4 hours. But it's tiny, tiny durations. And if we want to penetrate 100% with renewables, then our timescales for storage have to expand a lot. And I think they're up here. And you'll see why I think that. It's convenient for me to think that. I think they're up here in the order of 100 to 200 hours. 100 hours is 4 days. And part of the reason why I think that's very important is because we very often have a period of 4 days when the wind doesn't blow. And guess what? Our biggest resource in the UK is wind. So if you could, in very crude terms, put 100 hours of storage alongside your electricity system, you could run the whole place off wind, or maybe it's 200 hours. And some people will say, well, it's not possible because you need a seasonal energy storage, and that's not right. You know, that's not right. And here's why they say you need it, because this is energy demand over a 5-year period, well, 2006 to 2010 inclusive. And what you see is, this is just electricity demand, by the way, and I've normalized it. So what you see is demand indeed does rise quite a bit in the winter, and it comes down in the summer. But this is how much wind power we would have produced over the same period. Also normalized, but for some reason I normalized this to rated power rather than average power. It doesn't matter. The black line effectively represents average. And what you see is wind power is also seasonal. And the wind is strongest in winter, very obligingly, and it's perfectly in phase. So actually, if you put the right mix of wind power in your system, then most of the seasonal component that you would have needed on the electricity system goes away. And as we electrify more and consume other fuel types less, we need more and more wind proportionately in order to keep those in phase. But the long and the short of it is, you don't actually need seasonal energy storage, or not very much of it. Two statements here then. One thing is that one of the solutions to flexibility is put in a little bit of overcapacity. If we think about nuclear power, you could run the whole place on nuclear power, base load all the time, and just throw it away when you don't need, constant load, which is equivalent to our peak consumption, and throw away everything else that you don't need. Throw away everything you don't need, or don't use. And that's a way to provide flexibility, but it's an expensive way to provide flexibility. Providing overcapacity, nobody likes it. It doesn't sound nice to be able to collect energy and then not use it. But in fact, it's very economical to provide a small amount of overcapacity, particularly with renewables, because they're cheap. And we could and should do this. And you might ask the question, well, do we have enough resource? Yes, absolutely we have enough resource. We consume less than 350 terawatt hours per year. A report that came out in 2012 says we could generate 2,000 terawatt hours off the Crown Estate, basically, the water around the UK, all offshore if you wanted. So if you do that, and just to put a scale on things, you go back to your curves like this, you say, I'm going to run the whole place off wind. This is my annual demand, and this is the profile of wind over that period. And I'm going to add a little bit of extra capacity in order to make sure that I deal with the issue of not seasonal storage. You end up with a magnitude on energy storage, and in the order of 10 terawatt hours. If you want to run the whole place on renewables, 10 terawatt hours. It's not unthinkable. It's a lot, but it's not unthinkable. It's 10 days of our consumption, or 12 days of consumption. So, compressed air energy storage, what is it? Well, it's exergy storage. It is not energy storage. So if you think compressed air energy storage is energy storage, you're wrong. What happens when you compress some air, if you use 100 joules of work to compress air, and then you let that air come back to its original temperature, which you always do, nobody in their right mind stores hot air, exactly 100 joules of heat falls out of that air. And therefore, the net energy that you put into that air is zero. So you are not storing energy, you are storing exergy. The energy storage, the electricity storage technology that Yulong Ding and colleagues are associated with is even more amusing than this, because it stores negative energy, but positive exergy. Exergy is electricity for you. This is how much exergy you can store in compressed air. This is the formula. It's not particularly relevant, but R is the pressure ratio. And what you see here is that high pressure ratios are good. So the cost of your pressure vessel is more or less proportional to V times R. And this, the value of your vessel is more than V times R. So basically, increasing pressure ratio tends to be good. Here's a couple of simple numbers. 41 cubic meters of air storage at 200 bar, at 200 times atmosphere, is 1 megawatt hour. And I've had people tell me that you can dig a cavern, a hard rock cavern, for about 50 pounds a meter cubed. So if I do a very rough mental arithmetic, 50 times 41 is about £2,000. Well, that much in lithium-ion batteries will cost you £200,000. So £2,000 is a very, very good deal. So you get a hint of where I'm going with this. If we wanted to store our 10 terawatt hours, you need, well, nearly 1,000 million cubic meters of storage at 100 bar, which sounds like a lot, but in fact, caverns are quite big. So caverns typically are 250,000 cubic meters of storage anyway. So that's not unthinkable. Right, this is what CAS also is. It always involves heat. So what you do is you take exergy from a shaft, you turn a compressor, and you get two things coming out. You get high pressure air coming out, you hope, and you also get heat. And that tends to dominate the cost of your system. This is very inexpensive. So high pressure air store will dominate the cost of your system, generally speaking. That's kind of interesting. And there's a few different options for the high pressure store. So one option for the high pressure store is tanks, and I won't go through the numbers here, but you can get quotes from China that will say, we'll sell you tanks that are storing air at 250 bar, and they're about $80 per kilowatt hour, which is about a third of the cost of a lithium-ion battery. But of course, the tanks don't convert the energy for you, and the battery does. Or you can store it underwater. This was my entry into the whole area, and I had this idea when I was driving on the motorway, and that was in early 2005. And I set myself a mission to get this stupid idea out of my head, and I regret to tell you that I have still not managed to detach myself from this idea. It's a superb idea, as it turns out, which I wish it weren't. But for us, it's only any good if you've got 500 meters of water, because you want to be talking about 50 bar at least for your compressed air. And I'm in the worst possible place in the whole world to have had this idea, because all of this is shallow water and you have to go all the way out here to get to 500 meters. Almost everywhere else in the world has deep water close to shore. The entire Mediterranean has deep water very close to shore. And then the main relevance to here is geology, of course, and you can store in geological formations, and there is more than one reference that suggests you can get below $5 per kilowatt hour, and I referred to £2 per kilowatt hour earlier on when I was talking about 200 bar storage. So finishing off what CAS is, well, it has separate components of cost for the energy. Okay, I'm going to run over a little and sacrifice the questions. Okay, he's going to cut me off. It has separate components of cost for the power and the energy storage, and compression machinery is very well established in the range 1 to 12 bar. Yeah, and long lifetimes. Yeah, I guess that's mainly the important point here, is that the kit is characterized by extremely long lifetimes. What it is not, okay, we're going to blaze through some of this. It's not easily understood by anyone. Just because you've got A-level physics, you don't understand compressed air energy storage. It's not a mature technology. There are two grid-scale plants that have existed for decades. Both of them are prototypes. Neither of them was designed for the energy system of today. So people who extrapolate from those are simply talking rubbish. It is not inefficient. This is what compressed air does. It takes in electricity, and the two plant that I speak about, it takes in heat as well, and it produces electricity out. And people take the electricity out, and they divide it by the sum of these two energies. And they're both energy, but they're not both exergy. So they're adding apples and oranges together on the bottom line, and that is wrong. And people get numbers like 54%, and that's completely wrong. And the better of these, the two existing plant, properly calculated, is 79%. And okay, so I'm going to skip a couple of slides, never mind about all that. Here's the underground potential energy storage capacity. We ran an event as part of this EPSRC project back in 2016 entitled The Future of CAES. BGS was working with us on that, and essentially we came up with a measure that for one particular cavern that's presently used for gas storage, you could store 66 gigawatt hours of electricity just in the air, no thermal storage. And if you look at the country as a whole, well, you can store a lot more than that. With 1% of available salt beds, and this is only looking at salt, we had 5 terawatt hours. And it's a lot bigger than that. So to some extent, the key message here is there's a huge amount of it out there. It integrates extremely well with loads and generators, never mind this. You could compress air directly with a wind turbine, and people have proposed that, and that's a crazy idea because air pressure is so low, ambient pressure is so low that you need a very complex machinery to do it. But this is more interesting. You could have an electrically driven compressor to make 20 bar air and then take that into a wind turbine. And now you're dealing with air that's at a reasonable pressure. And it's very practical to do that. So you could convert your 20 bar air into 200 bar air and store that in a cavern. And now you're rather like what Toby was talking about, make COOLF directly for using COOLF or store COOLF. Use the work directly to compress something and store that. So next steps, well, most important, there is an International Compressed Air Energy Storage Alliance established. I'm the reluctant chairman of that. It was established on July the 3rd of last year. This was the group that was present in China at its establishment, but we had 40 organizations ringing into that, and that's carrying on, so you'll hear more of that. And we'd like to emulate the excellent work that was done by the CCUS task force by doing a kind of similar study to point out the opportunities that are available. There are some important remaining challenges. How do you form caverns? Controlling the shape, so not just arbitrary shaped caverns, but nice cylindrical ones. How do you seal them? In case you've got mud layers in there, how do you get hot compression machines? Can you reverse turbo machines because you never compress and expand at the same time? And so forth. Hydraulic compensations, keep the cavern at a constant pressure if you can. And then this is a book that I contributed to in 2016. This is a conference that I run every year. It's called Offshore Energy and Storage. I'm hoping I can persuade some people from here to come along to that. This is the leading conference on underwater compressed air energy storage. And our next steps at Nottingham are carrying on the good work. Thanks very much indeed.
Okay, Seamus, thanks very much. As I said, an enthusiast for the work. That's good. So questions on what K's can do for us? Who's going to go first? Oh, yeah, over there. Thank you.
Hi, I'm Andrew Bloodworth from BGS. You flashed up your challenges slide very quickly there. I think the other big challenge you've got is public acceptability. I think you shouldn't underestimate that. There are all sorts of very logical things we can do with the subsurface, and this is one of them. But the general public don't always see it that way, and politicians don't always see it that way either.
I do 100% agree with you. I will point out, however, that there are caverns where some lunatics put natural gas in. And hydrogen. So I did have a comment which was facetious on one of my articles about the underwater storage, which said something like, "This idiot will get us all killed. All that air will be released, and it will have an adverse effect." I agree with you. I'm being facetious, but it is a significant challenge. But we're talking about the same pressures as natural gas, so I should add that on the challenges.
Okay, thank you. This lady here.
Yeah, I'm not sure about the economies of scale on this, but have you thought about combining it with rigs, because you're offshore, deep marine rigs, would it be safe enough to provide electricity for offshore rigs in a small enough container subsurface that you could power a rig? I just think, does it work on those smaller scales, or does this have to be vast?
For underground caverns, one of the major keys is you have to think big scale, because the fixed cost part of it is extremely high and the marginal cost is extremely low. And so what you end up doing, if you're going to make a cavern, make a big one. For underwater storage, it's much more modularized, but you need deep water. So you're talking about at least 500 meters, as I say.
Because you're already drilling for your oil and gas? Could you not do some combined system?
Yeah, well, I'd like to put the underwater storage there and remove the drilling platform.
But you've got to power
Different
something.
stuff.
You've got to have a supply, don't you?
Yeah.
Okay, John behind there.
John Midgley, BGS. In a previous life and previous job, I was one of the people storing offshore gas onshore, considerable pressures in Denmark. I questioned some of your figures around costs, because what we found, the technical challenges and the different needs of materials from standard oil and gas adds a huge amount of cost to your bottom line for the well bore, the completion, and how you operate it at surface. And if it wasn't so bad using natural gas, but if you're putting compressed air in there, are you going to have to dry it before it's injected, or is it just air that goes in there, or is it filtered? Or I've no idea.
You can dry it before it's injected. That's a reasonable point. There's more to say about the cost than simply that.
Okay,
Sebastian Geiger from Herod Watt. It's not a geological question. Do you have any feeling of how much we can reduce that storage, the need for storage capacity, this 10 terawatt hours that you mentioned, by managing demand rather than supply? So your washing machine, your dishwasher going on when you're away from home, coupled to some smart apps that track the wind and go on when there's actually oversupply in wind energy, or...
Yeah, I think that for short duration storage, it mainly eats all of that market. You know, I think it basically eats the market for short duration stuff, because I'm very happy to do my washing 7 hours later. I'm not happy to leave my washing for a week or wait for a week to cook my dinner. So I do think that it has huge scope for short duration, but I don't think it plays significantly into the 200 hours.
I understand that the biggest need is large-scale compressed air storage, but you showed that intriguing small tank from China. Is there actually potential for small-scale compressed air storage in households? I mean, is there an economy in there?
You've got two different economies to worry about. One of them is the economy of the air storage, and one of them is the economy of the power conversion machinery. I'm working with a group looking at energy storage for EV charging stations, so it's not quite household. And part of the motivation for doing that is that if you take internal combustion engines that are retired from service as diesel engines, you can retask them to produce reversible compression machinery. And you can then, and they have negative value at the end of life, because the vehicle manufacturer is responsible for disposing of them. So at that case, they have a natural size, and it happens to be about 250 kilowatts. Much too big for a house, but good for a
smaller scale, but you've got to find
smaller
a compression
scale.
unit.
Absolutely. And it gets more interesting there, because if you do it small scale, you try to make sure you store as much exergy as possible in the form of heat, because that's much less expensive than the tanks. So the $80 per kilowatt hour was the cost of the tank. But if you couple a heat storage with it, you can store 2/3 of your exergy in the form of heat, and you can push that number down to certainly below 40. So I think that's interesting.
So I'm going to challenge you that you're not being ambitious enough, because to decarbonise in the future, we have to decarbonise heat. So it's the interseasonal challenge of heat, which could be 6 or 10 times the amount of storage, which you've talked about matching squiggles on electricity, and I'm interested in matching months and weeks on heat.
I fully agree with that. You know, one of the elephants in the room really is heating in the UK, certainly. And I absolutely agree with that. And the wind isn't that seasonal, so it won't do that. You know, obviously we'll replace the housing stock. Thermal energy storage works. Thermal energy, well, rather like Professor Peters said, you know, if you want to store the ability to make cold, just store cold. Yeah. If you want the ability to store heat. Large tanks of water cannot be beaten with insulation around them. You cannot beat them for storing heat that's fit for heating houses. So I think this has relatively limited interaction with that.
Okay, and last question, I think.
I think you've possibly just covered it, actually. I was just going to say, if I understand correctly, you're saying you've got heat as a byproduct. When you're actually releasing the compressed air, you have heat as a byproduct.
When you're compressing the air.
When you're compressing. So, okay, yeah, so within the cycle, you have a heat surplus produced.
Not within the tank. When you're compressing the air, heat comes out of it.
Yes, so you have heat coming out. Yeah, that heat that's coming out, is there any capacity there that it could be utilised within perhaps ground source systems that can provide local heating for areas? Could you utilise it, or do you require
Yes,
it at a later stage?
at small scale, what you would do is you'd store that heat locally and you'd put it all back into the air
To then release it.
to then get almost the same amount of electricity back out of it as you had done. I had a section that was about integrating it. Compressed air integrates extremely well, and it could be integrated with a local heating system where you throw out relatively low-grade heat that's valuable for greenhouses or something.
Great. Okay, thank you very much.
Thank you very much,
That's
Chairman.
good.